We studied the stability properties of differentiable maps in a previous lecture using the point of view of monopies. Indeed, we saw that several classes of differentiable maps, as for instance immersions, submersions, embeddings, or diffeomorphisms, are stable if the domain of definition of the differentiable maps is indeed a compact manifold. In the current lecture, we are going to see, again, we are going to deal again with these properties, but from the point of view of the topologies that we defined in the set of differentiable maps, and more precisely from the point of view of the external topology. Indeed, we will show that all these classes of differentiable maps, immersions, submersions, embeddings, diffeomorphisms, and others, defined open sets for the strong topology, and indeed that this property holds even if the domain of definition of the differentiable maps is no longer a compact manifold. Many relevant subsets of maps are open in the strong topology. The first example that we are going to consider is the set of immersions in the set of CR maps from M to N. So the first thing that we can say here is that we can suppose that R is equal to 1. And why is that? We have a property that is interesting, is that if we have U an open set of some CR, okay, of some space of CR maps from M to N with the strong topology, then the intersection of U and the space of CS differentiable maps is open. Of course, for the strong topology in CS. Okay. Of course, here we are considering that S is greater or equal than R. So if we have open sets for the CR topology, the intersection with CS with S greater or equal than R is going to be open in CS. And here we are always considering the strong topology. Okay? So in particular, if we prove that the set of C1 immersions from M to N is open in the set of C1 maps, then what we have is that the intersection, of that set of C1 immersions, okay, with the set of CR maps is indeed open, okay? Is open in the set of CR maps with the strong topology, just by using the previous remark. But the set of CR maps that are immersions, C1 immersions, is the set of CR immersions. And there we have the result that we want to prove. So we can suppose R equal to 1. That's not going to be an issue. Good. So we want to describe a neighborhood of any immersion. So the first thing is, let's fix an immersion, for instance, of class C1. And now we want to describe a neighborhood of F for the strong topology that consists uniquely of immersions. Okay? So what we are going to consider is here an atlas such that the family of domains, to be here a little bit more precise, something like this. Okay, an atlas of the manifold M such that the family of the domains is indeed locally finite, right? And we can suppose that the image of these domains by the map F is indeed contained in the domain of some local chart for the manifold N. Where C sub beta I is a local chart, okay, of N. That's not really a problem. What we just need is considering smaller UIs, and it's easy to obtain that. Okay, since we don't want to deal here with complicated indexes, what we are going to do is indeed saying that C sub I is equal to C sub beta I. Here should be beta I, and the same thing with the other elements in which the subindex beta I appears. Okay, so when beta I appears, we just replace it with I. Okay, it's just making the notation simpler. So now what we have is a family of local charts, okay, in which the domains we already know are locally finite. And we have another family of local charts, okay, for the manifold N, right? Now we can actually, these are the sets of charts that appear in the definition of a neighborhood of a differentiable map for this strong topology. Okay, we need now to consider the family of compact sets. So we're going to define a family of compact sets of M, family of compact subsets of M such that K sub I is contained in U sub I for any I. And moreover, that the union of all KIs is indeed the whole manifold. Those are the two properties that we are going to require. That is possible because the union of the UIs is indeed the whole manifold. Right? So we have the set of local charts for M, set of local charts for N, the family of compact sets. We have to define the family of positive real numbers too. Okay, and let's see how we do that. So consider A sub I, which is the set of differentials at X of the expression of the map F in local charts. And we are going to consider these differentials for X belonging to the compact set image of ki by phi sub I, right? What we have is that A sub I is contained in the set of linear transformations from Rm to Rn, right? But since F is actually an immersion, every element of AI is an injective linear transformation. Okay, so all elements of AI have maximal rank. And indeed, the rank is equal to M. Since this A sub I is a compact subset of the set of linear transformations, because this set over here is compact and our maps are at least C1, so the map that sends X to this differential in particular is continuous, then that implies that if we have a map T that belongs to AI, and okay, sorry. What I want to say is that there exists a real positive number such that if T belongs to A sub I and the norm of S minus T is smaller than delta sub I, obviously S is also a linear map from Rm to Rn, then necessarily S has maximal rank. This is because the set of linear maps of maximal rank is an open set. So what we get is that if now we consider this open neighborhood of F, in which we have the set of local charts phi for M, the set of local charts psi for N, the family of compact sets, and some family of positive real numbers that we didn't determine yet. Here, what we get are the C1 maps such that the differential of the expression of F in local charts minus the differential of the expression of G in local charts is smaller than epsilon I for all X that belongs to the image of Ki and for K equals 0 and 1. That's the set that we are considering. The previous discussion implies that if epsilon I is small enough, then any G that belongs to this set satisfies that the differential of G in X is injective for any X in Ki. Indeed, it could be the differential of this map in any point in this image, but those things are equivalent. So we are going to consider epsilon I small enough for every I, okay? And in that way, by considering epsilon sub I small enough for any index, what we get is that if G belongs to that open neighborhood of F that we were just considering, then the differential of G at the point X is injective. For every point in Ki and for every I. But the union of the Ki's is M. So this implies that the differential of G at the point X is injective for every point X in M, and this implies that G is an immersion. And so we proved that there exists a neighborhood of the map F that consists exclusively of immersions. And so immersions defined an open subset of the set of CR differentiable maps. Let us see that the set of CR submersions is open in the set of CR maps. Okay, let's give the idea. What we used in the previous proof in order to show that the set of immersions is open for the strong topology is the following fact, is that if we consider the linear maps from Rm to Rm such that the rank of T is maximal, this set is indeed open. And we use this fact for the case in which M is less or equal than N. But if we use it now for the case where M is greater or equal than N, then by proceeding very, very similarly as we do in the case of immersions, we show also that submersions define an open set. These proofs are very, very similar. In this lecture, we considered the set of CR differentiable maps between two differentiable manifolds, and in particular, two of its distinguished subsets, namely the subsets of immersions and submersions. And we saw that these two sets are open for the strong topology. In next lecture, we are going to see that the set of embeddings, of CR embeddings between two differentiable manifolds is also open in the set of differentiable maps. Thank you for your attention.